So last time with the 6502 emulator, we just did bit, which does a bit test. We just implemented this instruction. And while I was watching the video back, I thought there was a few things in here that didn't look right, but the tests were passing. And I think it was this. It was the program status is supposed to have the, what is it? The program status is supposed to have bit 6 and 7 of the value from memory copied into those flags. And I was ORing them here, and I'm pretty sure that's wrong and that shouldn't work. But all of our tests pass. So what that probably means is that the tests aren't good enough to catch that I'm doing that wrong. So if I can change these tests and make that break, then that probably means that I wrote that wrong. So let's just try to see if I can do that. So these are all our test bits. So this is the first one, test bit 0 page. So that should put a true and true into the negative and overflow. Sorry, negative. Yeah, negative and overflow flag. So I'm just going to make sure that these are set to the opposite. I'm going to make sure these are set to the opposite before this test starts. Just for a bit of a sanity check, because essentially this shouldn't make any difference to the test. That should still pass. I think this one will though. Yeah, so that's still passed. I think it's the case where these can come out false if the flags were true prior to that, like this one. I think that's going to fail. So again, this shouldn't change the outcome. This should still be false, and it's failed. So I would say these tests just need to set these flags here to be, at the very least, the opposite of what they're expected in there. So V is expected to be true, so we'll set it to false, and N is expected to be false, so we set that to true. So I'm just going to force all these tests to fail, or just make as many fail as I can. Let's do that one to true. And this one's the mix. Right, so what did that do to our bit test? And the answer is it made 4 of the tests fail. So that shows that the power of not writing very good tests means that you can actually write code that looks like it's working, but actually it's not. But the good news is that all we have to do is improve the test, and now we can go back and improve the code. So the thing I did wrong was I was ORing this, and I shouldn't really be ORing it, because if the processor status already had a 1 in that flag before and these were supposed to be 0, it would keep the 1, and we don't want to do that. We want to just set it to the actual value that is in memory. So I don't believe we can do this way. I'm not sure what the best way to do this is. I suppose this way would work if we did the negative flag. So that just sets the negative flag. Is that right? Well, we'll see. And the overflow flag gets set like that. I think that's the overflow flag. And in theory, that's the same down there. Oh, that's made more tests fail. Oh dear. So that's not the way to do that. I think, is it, are we supposed to do it like that? Ah, there we go. So that's just setting the value of these bit fields. I might just bring out these into some, constants, just so it makes more sense when you're reading these what this actually is, because we've used this like negative bit field all over the place. So this one is the And we've got the overflow flag bit. Should think is that one. So I just want to make it a bit clearer when I'm using these, what exactly that is. So they're bit masks basically, and this one is the overflow flag, yeah. Right, and I think I've used that in some other places in here maybe. So I thought the next thing to do might be to just have a break from putting any more instructions in and see if I can write a little program that can actually use these instructions that we have written. So this will be a bit crazy, but what I have done is I have got Turbo Assembler, this TMPX. Yeah, so that's this. So I've downloaded this Turbo Assembler, which is just a 6502 assembler, and I've got it set up here in Visual Studio Code just to compile a program. And I've actually got this, found this page here that tells me about when this compiles, what does it actually make. So yeah, Commodore 64 program, and they are, it is ridiculously simple. It actually says there, it literally has a little endian word at the front of the compiled file that tells you where in memory do you load this file to, and then after that it's the file, and that is the entire program format, which is absolutely crazy. So to do a turbo assembler, well, to do 6502 assembler in here, this star just means this is where the first part of the program is going to go to, so that'll be hex 1000. So basically that will end up being the first 2 bytes of the program, is saying load it into here. So it kind of sets where you want the program to be, and then you can just start writing stuff. So we've got LDA working, and I think you do hash for immediate and $. So, and then I can load an 8-bit. This loads an 8-bit hex value straight into the A register, and then I've got this set up to just compile, just using this. So just compiling test code, and it spits out test code program. So that's really it. So this creates my program, and I'm just going to open this in here. This has got hex editor, and then we can take a look at it. There is the little endian 1000. That was this. There's the 1000 in hex. So the first 2 bytes are that. The least significant byte is stored first. In fact, this has got a little endian helper over here, and it's actually showing it to me there. It's 4096 if it was a little endian hex number, and it's converted it to decimal for me there. So our program gets loaded to 4096. A9, that is the opcode for LDA, and there's the FF. There is the FF that I loaded into that I want loaded into the A register. And weirdly, it says there's a plus here. Or sorry, it says there's a 0 at the end of this file, but actually there isn't. For some reason, this hex editor just shows a 0 at the end of the file when there isn't actually one. I think it's just put one there. So in theory, that's a good program. We might as well actually just put a little bit more in here. So if I just do that's just a label in the program, and we implement a jump, and I can jump to the label. So in theory that works too. And what else can I do? I can store the accumulator. Well, I could store the accumulator back into memory. So I could store it somewhere in the 0 page. I could store it at 90 in the 0 page, and I could actually also store it at 8000 in memory. I think that's a good program, is it? Okay, there we go. So that has compiled. So let's just have a quick look at that. So I'm not going to check that, but yeah, you can kind of see that's part of the program. What have I got? Where's the 8000 in there somewhere? There it is. There's the little endian 8000. So that looks like a half decent program. So we will load the accumulator with FF. We'll store it in 90 in the 0 page. Then we will store it at 8000. Then we'll go back to start, and we'll keep looping over that. And is there anything else we could do? Maybe we could do our exclusive OR. We could exclusive OR the A register. Maybe we'll do this. We'll load the accumulator there. Then we'll have the start. Then we'll store it at 90. We'll store 8000. We'll exclusive OR it with CC value. So we're going to exclusive all the A register, then we're going to go back, and then we're going to store again. So maybe if we get lucky here, the A register will keep changing and we'll get different values in memory. But the first one would be 90. The first one would be FF stored there. Then let's put something. So anyway, at least it'll be different on 2 of the loops. So I don't exactly know what that'll do, but I suppose we can find out. That is a good enough program to try and load in. So what I'm going to do is I'm just going to, I don't want to load this for now. What I want to do is just paste this in. So I'll just do a find and replace on this. I'll find and replace all the spaces, and I'll replace them with comma like that, and that. There you go, there's my program. I'm going to inline it straight into our program. Maybe we'll do this as a little I'll probably just run this as a unit test for now. Okay, so let's put that. I'm just going to put this in the end of here for now, but we could move it later if we wanted to. How's this going to work? Right. Just so you can see it all. There's our little program. Our little compiled program. What I'd really like to do is load program. And we want to take in the number of bytes that is. So we want to load a program. It's 14 bytes long, and then we want to execute. Well, we want to execute quite a lot of cycles. I'm going to put a little while loop in here. Call that clock. How many cycles do we want to do in a go? 20. And we'll take in the memory. And then we will so that in theory will loop round for 10,000 cycles, and then I don't know what we expect. This isn't really a proper test. I'm just, what do we expect at the end? I don't know, but this is really what we need. We need to be able to load this program in. And that's the bit that we don't really have. So I'll move this out into its own test if this is a success. So really, we want to write this load program. So this is probably another one that doesn't want to be in the header because it might end up being complicated. There we go. If only it were that easy. So am I down to just a linker error here? Yeah, linker error, unresolved external. So let's go down below here and all this stuff. Let's attempt to load a program. Suppose we're going to have to take in the we're going to have to take in the memory as well, aren't we? Right, does that compile now? No, because these are unreferenced parameters. So that's fine. So we could assert if the program's not valid, but we are not going to do that. We are going to have the position that we're at reading the program, and yeah, start at 0. Let's get the load address. Because remember, the first 2 bytes are a little endian. Let's do it like this. We have to make sure number of bytes is greater than 2 as well, otherwise what's the point in even loading this? So the low end is first, and that gets shifted by 8. So that is our load address. That's the first thing. And then the rest of the program just gets pumped into memory, and I'm not going to do anything fancy again. I'm going to just copy the bytes in for now. We can actually do, we could do it like this. Well, I is less than the load address plus number of bytes minus 2. And is that right? That could be right. And then we just pump that data into memory. I think that could be even right, I don't know. Except the function does not take 2 arguments down here. Well, so I suppose that really we don't even need to execute this to start with. We could verify that the program is correct. I think what I want to do is, it's given that program. Let's actually just make something that can load a program into the correct area of memory. Let's not try and execute it just yet, but we'll keep this code for now. So given a program, if we try and load it into memory, then we expect that it's in memory. So we could actually just look at that. So what I could do is, I'm expecting that at 1000, that's the first byte of the program, so I'm expecting A9 to be there. The byte just before that, because I know that we zeroed the memory, I expect that to be 0. And then we took the first 2 bytes of that program, and then we started loading that one in at that address. And then we expect the next byte to be FF, and then we expect the next byte to be 85, and so on and so forth. And we don't have to, we could test all those if we wanted to, but I'll actually just assume that the middle's okay. And then we'll get, so that will be 1000, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9, A, B. There we go. B. So I'm expecting B to be 10, and I'm expecting C to be 0 because that's the end. So A, 1000 A should be 2. And 1009 should be 4C. So that is what we expect if we haven't overwritten any memory or done anything bad. So this isn't testing that we can execute this program. This is just testing that we can load this program. Let's see what this does. That actually worked. So that bit of code in there is actually doing the right thing. It's actually loading the programming correctly. At least we think it is. Oh, wait a minute. Whoops. Didn't actually do any tests in that test. I actually just set the memory to what it was. That's really stupid. Right, let's try this again. Why did I do it like that? Oops. This is more like it. What was I thinking? Right, that's more like it. Let's get rid of that now. We've got that down there if we need it. Okay, let's try that again. Does this work? No, it doesn't. I was quite shocked that that worked first time. I was like, wow, I've written a test that works first time, but it didn't actually have any tests in it. It did not load it into memory. Really? It was 0. And we wanted it to be loaded with 169, which is the A9 value, is it? Okay, so that didn't work at all. Let's try, see what I did in here then. Cool. We've got everything right here. We've got number of bytes, got the program. Load address is 0. Why? Why is it 0? That's not right. Is it because these things are words and it has to be promoted? Does that need to be promoted to a word before I do this? One of these, is that the problem? Does this need to be silently, not like that, like that? Let's try that again. Yeah, I think maybe this number was getting shifted off because it was a byte and it wasn't working. Load address should be 1000. No, didn't get that right at all. What is wrong with this? That should take program at the address of 0, use it, then increment it, and then do the same thing for the next one. Am I missing something here? Is it an order of operation thing? Is it this? I'm being screwed by something here. No. It's definitely not. That should be... What's wrong with that then? I actually don't know what's wrong with this. So let's take these out into their own. That's the low byte, that's the high byte. It should be the low byte ORed with the high byte. Okay, let's try that again. Let's just sanity check this thing. Low byte is 0, high byte is 1000. We OR those together, we get 1000. What was wrong with that? Were they not getting promoted to a word properly? I'm pretty sure that's exactly what I just did. Anyway, maybe this test passes now. Oops, let's just see. Where are you? Yeah, it did. Okay, so it was just that accidentally somehow being stuck as a byte when it should have been a word. But other than that, and yes, you could do a mem copy in here or something like that. There you go, but I'm not going to do that now. So I tell you what, since we've come this far, let's actually make a unit test file for this. So the next thing is I'm probably going to use this program twice. So let's just kind of stick that up here. Am I allowed to do that? Where can I put this where it will allow me to do it? Can you do it there? Yeah. Okay. Is this still a running test now? Yeah, so nothing changed except I've just put it in its own file to make this, in case this gets expanded a lot. I might just also copy that in there as well, just so we know what it is. So we just got a little like knowing what those bytes are for the test program because it's been compiled. And let's do the same thing and we'll execute it this time. Also, let's pass that in like that. There you go. So in theory that doesn't change the program either. It's actually just working with the memory. So yeah. Does that still run? Oh. Okay. Oh, I know what's happened here. So the execution didn't work. I know why. Because it is, what is the, yeah, the problem with this is after we've loaded it in, the program counter needs to be set to where we want to start executing. Now I doubt that load program should do that, so I'm just going to set it right here. In fact, I might return the address just for convenience. Should I do that? I don't know if this is a good idea. But I am going to return the address that we loaded the program into, just so that I can use it again for doing these tests. See, this is the weird thing, because it's 0 if no program. But actually, like 0 is a valid pointer in the C60, well, in the 6502. So I don't know if that's a good thing, but that's what I'm doing. So that's where I want to start executing from. So this is a bit of a fudge, but I think that's as good an idea as any. So what's this going to do? Is this actually going to execute a program that we wrote? And the answer is it's stuck. It's stuck in a loop forever. What's it doing in here? Oh dear. This clock has gone, it's gone bad. Oh dear, that's not good. What's happening to this clock? Is it decrementing? I think it's wrapped. Oh, maybe that's what's happened. I think it's wrapped. As well, the clock is, yeah, greater than 0, and I think it wrapped I think it went down to near to 0, then wrapped around to above 0, and now it's going around forever. So let's just try that. Is this gonna... Oh! That actually worked. Wow. So, as a little test, I wonder if I can do this. After each 20 cycles, let's just try and run as few as possible. Let's just try and run one, because each time it runs one, it will always, this is designed to always try and go through one whole instruction. Let's actually just print out and see what we get. I don't know what's going to happen here. What have we got there? What is that? Let's put a line break on the end of that, because that is absolutely mental. I don't know what I'm looking at. Oh, the air register's changing. Well, I think we wrote a program. I think. Let's look at the program counter. Let's see what that's doing. Oh, we can put that on the same line, really, can't we? This is kind of like, this here, what I'm doing is kind of the beginning of a debugger. You know, just getting some information out about what is it doing. Don't want that now. I'm probably going to take this out, but this is just for fun, really. So is it looping? 4105, 409, 98, 100, 103, 105, 4098, 100, 103, 40. Yeah, so it is doing its jump. The jump instructions running. And it looks like that exclusive OR that put in is actually doing something. So that's actually executing code. That is unbelievable. What else can we get out of this? I mean, we can just print out the... don't know that the stack point is not getting used in this. Let's just print out some. We've got program counter, stack pointer, and let's print out A, X, and Y as well. I don't think I used those in this program, but in theory they shouldn't change. Yeah, they're not changing. And stack point is not changing either, which is good because we didn't use the stack. We just did a jump and that doesn't use the stack. I think this is a good test, even though it doesn't actually do any expects. It does just make sure that we don't go into an infinite loop. We just execute this for 10,000 clock cycles and then we exit. So however many, I mean, we could do a lot less than that. We could do like 1,000. But we're not verifying that anything in there is correct because we don't really know what the correct state is after each one of these executions because we're just executing a whole program there. That's a good start for something that can actually, you know, print out the status of the program. Yeah. So let's call that. I think I'll move. Yeah. So I'll just keep that code for now. But I'm not going to use it anyway yet, but it might come in useful later. Is that going to compile? No, because you want the definition of it. Declaration. Actually, we can also put the flags in there as well, can't we? Let's just, I'm going to print them out as one thing for now because I can do that. But again, this is just something we can improve later. Processor status. So this might come in handy for future testing and stuff when we're trying to figure out what the hell is going on. Yeah, processor status is not changing. But again, I don't expect that because it will, yeah, I don't think it's getting anything in there that's supposed to change it. So that was just a little bit of a kind of get an idea of, you know, where we are with the actual emulator and does it actually work. And we only tested a few of the instructions we've actually even written there, but we tested 1, 2, 3, 4. I mean, actually, let's just go back and try this again. If we just execute one clock cycle, we should have an FF in the A register at the end of this, shouldn't we? Yeah, 255. The A register's got 255 in it. So yeah, it looks to me very much like, just looks to me very much like that we can now actually load a program, at least a program that we already have the bytes for that we've somehow put into memory, because these ones I've just hacked into the program. But I would do that for testing really. I don't want to load files in the middle of a unit test. So there's a tiny little program that is basically that thing there above it. That's really cool. So next time I'll just keep going and put some more instructions in the emulator, because I suppose this is one of the problems with these kind of emulators is that I can only write, at the moment it'll only ever be able to run code that I've written, like 6502 code that I've written. And the reason for that is that it's not complete, and until every single instruction is complete, it will never successfully be able to execute a program that was written, you know, prior to this emulator being written, because it has to be able to handle every single possible thing that the 6502 could do. And also, to make matters worse, it might have to handle things that the 6502 wasn't supposed to do, meaning illegal opcodes, which some people did use because they knew their specific machine had a specific processor, and they knew the illegal opcode would do something weird, so they used it. So that's really bad, but you've got to deal with the legal ones first before you even think about the illegal ones, I think. So next time we'll just move on with some more of these instructions, and I don't know which ones to do next. Transfer registers we've not done, and they're quite easy, so we could move on to those. Yep, right, so catch you in the next one.